Greetings. In this one I'll be talking about the concept of stabilizer in the context of group actions. We talked about group actions in the previous one. We've also talked about permutations as well as cycle notation for permutation. So these three things are definitely I recommend to know first before going to this topic. So I will not explain these topics in detail in this one. So let's say we have a group action. This is notation just written out to revise quickly, but I'm not going to go into the idea of group actions. We basically have this two tuple as input, and output is something from the set X. X is some set on which the group G, which is here, so-called acts. So group G acts on X, and the result goes into the set X again. So we have basically, we're using the operation of the group and the elements of the group, and we put in them in operation with the elements of this set which is outside the group. So this is the kind of idea. Or of course you can act on the group itself. So the elements inside the set on which the group acts can be equal to the elements already inside the group, or some can be same or something, but yeah, anyway. So the idea of a stabilizer is this. If we have a stabilizer, we denote it G sub X. It's some for lowercase x inside the X set, in the set X, on which the group acts. We have Gx is the stabilizer and is defined as the elements of G for that concrete X, when the group acts on that element, the element stays unchanged. So it's basically the elements of the group for a chosen, we choose an element inside the set on which the group acts, and want to see for which elements of the group which act on it, this chosen element from that set on which the group acts, some element X, we choose that element, for which elements of the group the group acts on it as the identity. Of course, the identity element, there must be an identity element that acts on all elements of the set on which the group acts as a non-changing element that doesn't change the element, leaves it the same, but perhaps there's more. There is more than trivial. Okay, so the trivial case is of course the identity element itself, but it can be more perhaps. So let's see. So let's, for example, talk about the example of permutations on three letters, symmetric group S sub 3 perhaps, written as such. And the notation of permutation is like the first line and the second line is the permutated order of the numbers. Again, I said permutations and cycle notation I'm not going to go into again because we've done it previously. It's definitely recommended to know first before going here. So let's just list out this. There's 6 elements to S3. So this first element, I'm just changing the order of the numbers in the second line. In the these permutations, that's the whole idea. But still, it's definitely good to know it before going to this topic, right? So I'm not going to focus on explaining that. All right, so we have this. The first line is C. The first row, of course, is the same. All right, and each of these permutations can have their cycle notation, so I can write it also as cycle notation. This is the identity element, so I can see E, say E. I can just write out the elements in cycle notation, which is far more compact as far as writing it. So you can say, okay, S3 consists of elements. The identity element changes not the order, then this element is 2, 3 as a cycle notation. This element is 1, 2, 3 as a cycle. This element is 1, 2 as a cycle. This element is 1, 3, and this element is 1, 3, 2. So these are our 6 elements of this permutation group, permutations of 3 letters. And now I'm asking, if I choose one of them element, one of these elements, one of them, then which elements of the group G which acts on it, from the set X, which is not this set, but from this set, from the set X, which elements of the group G will not change it? Well, first of all, let's also give an example of the set X, right? So it doesn't have to be the same as the elements of the group. I mean, it can be the numbers themselves. So 1, 2, 3. Let's say that's the set X on which the group will act. So now let's say I choose X to be. It can be either of these 3, any of these 3. So let's say I will choose number 1. So then it will be written as G sub 1, the stabilizer of the element 1 for the set X. So inside the set X, I choose lowercase x in X, equal to 1. Okay, so I choose number 1 from X. Now I let G act on number 1. And I define this action is going to be the way that basically if you have a permutation, if I choose a number, what that permutation assigns for that number will be the result of the action. So for example, this permutation for 1, it will give 1 again. So I see identity, of course, is part of the stabilizer. So the stabilizer will be a subset of the from this set, all right? So let's see. We will write it out as a set. So which elements? So just to repeat once again, these are the elements of the set X, and the group acts on them. And I say, how is it acted on? Well, if you take a number from here, look at the concrete permutation depending on which you choose as an element from G, because G will, with all its elements, act on all these 3 elements. Based on what that permutation gives for that chosen element, that's the result. So for example, this permutation, if I choose 1, says, oh, 1 goes to 3. So the result for with the action by this element on this element will be 3. And again, if I put 1 into this permutation, it gives out 1. Alright, so let's see, therefore, which elements will not change it. Which elements for element 1, stabilizer of 1, will output 1 again? Well, this permutation does, because it leaves it. This permutation does. So, okay, so for this example, this is the only example we're now looking at, we can take up the board and circle what we've written out here. So either we can circle it out in this permutation notation, in the two-row notation, or in this simpler cycle notation, doesn't matter. I mean, I can start with this one and also we can trace it back here. So which elements of the group do not change this X equals 1, G sub 1, stabilizer of 1? What is the set? Well, it's the set of this element, because this one goes 1 to 1. It's any element that goes back to 1. That only changes the other numbers, not 1 itself, because we chose stabilizer of 1. And this one also. And all these other ones change 1. This one will give 2 for 1, this 3, 3, 2. So that's different. So these 2. So it's a non-trivial stabilizer, and it's the identity element and this one. And which one was this one? It was the cycle 1, it was the cycle 2, 3. So what you see with cycles, I mean, if we choose a concrete number from this set and looking for the set stabilizer, it will be the subset of the group's elements which do not change the number itself, if in this concrete case. So, I mean, for 2, it again will be cycles that do not take into consideration 2 when you read the cycle. I mean, for example, 1, 3 moves 1 and 3, but it leaves 2 at the same place. All right. So, for example, the stabilizer for, we can do stabilizers for the other 2 as well, just for practice. So, which permutations leave 2 same? Which elements of G, when acting on the set on the element 2 from X, leave it the same? Well, it's this one and this one. So of course it's the identity again. It's always identity and one more here in this case. So it's gonna be 1, 3. Right? 1 and 3 are exchanged, but 2 is left. The cycle 1, 3. This cycle notation represents this permutation. And which elements of the group, when acting on the element 3 from X, make it not let it stay the same? Well, again, the identity, of course, the identity permutation, and it's gonna be leave 3, so it's 1, 2. Element 1, 2. All right. So that's that. So this one and this one for G sub 3, or the stabilizer of the element 3 from X.